In this video, we will be introducing polar coordinates. Up to this point, when we've been graphing a point, we've graphed on a rectangular coordinate plane, our Cartesian plane, meaning our x-axis and our y-axis were rectangular, and we would go right and up to a given point, or left and up, or left and down, and so forth. So the Cartesian plane is what we're used to, and it's a rectangular coordinate system. Now with polar coordinates, you'll see that the graph paper looks a lot different. So if you prefer to use graph paper, polar graph paper, it's going to look different depending on what you find or download, or if you were to Google polar graph paper. They have all different kinds out there. This is one kind that I found, and in order to familiarize ourselves with this polar coordinate plane, it's helpful if we first find our 0. So I'm going to choose to let this vector be 0 degrees. Now you'll notice that I can also find 90 on this plane. 90 degrees would be along this vector. And you could go on then and show that this one is 180 degrees. And then this one would be 270 degrees. And you get that by just continuously adding 90 plus 90 is 180, plus another 90 is 270, and then we could go ahead and call this one 360, but we'll stay with 0 for right now. Now to designate a point on the polar coordinate plane, I'm going to just pick a point just randomly right here, something on a line that I can show. This point, notice that coming out from this, what we call the origin, we have to come out 1. So this is 1 unit, and then this one is 2 units, and this one is 3 units, and 4 units, and 5 units. So the distance that we come out on this line is 5 units. And then we have to give an angular rotation. Okay, now notice that, we'll say that 5 for a moment. Notice on this particular graph paper, our 90 degrees is split into 3 pieces, equal pieces. So this line right here represents 30 degrees, because 90 divided by 3 is 30. And then this line represents 60. Okay? And that's all because if you look at this right around this center circle, our 90 degrees is divided into 3 equal pieces. So those vectors represent 30 degrees. And then another 30 degrees would be 60. And then another 30 degrees puts me up at my 90. So whenever you initially find some polar graph paper, you need to ask yourself, what do these angle measures represent? Okay. Then now you'll also notice that this 30 degrees is divided into 1, 2, 3, 4 equal parts. So that means half of that 30 is 15. And then this line would be 7.5 if we were going to want to use it, but 7.5 degrees. What we're actually dealing with here is polar graph paper that would be best used with radian measure, but we haven't learned about radian measure yet, so let's just stick with the degrees. So this one is 15 degrees, and this one is 30, and then another 15 degrees would put me at 45 degrees, and then another 30 would put me, another 15 degrees would put me at 60, and then another 15 degrees would put me at 75. So that gives you an idea of what these rotations represent. And it makes sense now because this vector right here is halfway between 0 and 90. So it makes sense that it would be a 45 degree rotation along this from our 0 up to this mark right here. Okay. So now to label this point that I chose right here, the way you label a point, the polar coordinates, so to speak, is you first give the distance from this center point. So we counted off 5 units. So that distance is 5, comma, and then the second measure that you give is the amount of rotation from this 0 degrees right here. So since we said that this vector was 30 degrees right here, then this point is best represented by the coordinates 5, comma, 30 degrees. Now in our textbook, which our textbook is the only textbook that I've ever seen it shown this way, but our textbook shows these coordinates as 5, 30. So if you want, you may write your coordinates as 5, 30, like this, or you can write them this way to match the way the textbook writes them. Either way, I'll try to use both notations, but I really have never seen this notation anywhere else but in this particular textbook that we use. Alright, so if I were going to give coordinates for this point right here, the first one that you write is how far away from the center line you're coming. So here we have 1, 2, 3, 4, 5, 6, 7, 8. So it would be 8, comma, and then we can see that the rotation is going to be from 0, you always go from 0, up to the point. So our angle of rotation is 60 degrees. And in our textbook, they would write that as 8 and then 60. Now, you'll notice that if you choose to graph a point that's over here in the second quadrant, let's say, for example, we want to give coordinates for this point right here. Again, we need to figure out how far from the center point we're going to go out. So even though there's no line shown, I'm still going to go out 1 circle, 2 circle, 3, 4. So my first number that I'm going to write is 4. And then I need to figure out the angle that I'm rotating from the 0 around to when I hit that point. So remember, every 2 of these was 15 degrees. So add another 15 degrees onto 90. That puts me at 105 for this vector. And then add another 15 onto that to get this one. That'll be 120 degrees. And then add another 15 onto that. Should get me to the vector that I'm wanting. Yes, it does. Okay. So adding another 15 onto 120 puts me at 130 degrees. So this point is at 4 units away from the center point and 130 degrees rotation. So in our book it would be shown as 4, 130. So most people, when they're doing the mathematics involved that's necessary for polar graphing, for example, if we were asked to graph the point 430, and again that could be 4, 30 degrees. We would draw our 0, this is 0 and there's 90 and so forth, but keeping now in mind that this is a polar coordinate. This is a point that's written in polar coordinates. So first we want to estimate about 30-degree rotation. So 30-degree rotation is going to be about here, but to label that so that you're not wondering what that is, you always write your angle of rotation in here. Okay. And then out here on the distance from the center point to the point that we're talking about, that we are going to label as 4. So you don't have to be exact as far as the angle measure that you rotate, as long as you label it 30. Now, be aware though that if your angle is something like 160, you don't want to put that in quadrant 1. 160 is going to have to be over here in quadrant 2. Okay. Now, notice that we have a relationship between the polar graph, the 430, and the coordinates written in rectangular form. Okay, remember rectangular form goes right, some amount, x, and then up, some amount, y. And from a rectangular point of view then, we can give this point a name. Right now we said it was 430, but we can figure out what x and y is using our right triangle trig. Or we can use the 30, 60, 90 triangle information that we know. Remember that if you have a 30, 60, 90 triangle, the side opposite the 30 is half the hypotenuse. So my y value should be 2. But if it's not a 30, 60, 90, remember that you can use your right triangle trig. My y is the side opposite, and I know my hypotenuse. So I can say then that the sine of 30 is equal to the side opposite over the hypotenuse. This is just definition of the sine function. And then to find y, we multiply both sides by 4. Our 4's cancel on this side. And so we see that y is equal to 4 times the sine of 30. Now if we get our calculator, make sure we're in degrees. Okay, good. So 4 times the sine of 30 gives us 2. So y is 2. All right. Now, so it was faster knowing our 30, 60, 90 triangle information, but again, that's not something that you have to do if you have a calculator available. But it's much faster and more accurate if you do. Okay. My x value on a 30, 60, 90 triangle, this x is opposite the 60-degree angle, or it's adjacent to the 30-degree angle. So I can use cosine function since the x is adjacent to the angle that I'm given here. So I can write cosine of 30 is equal to x over 4. Because remember, cosine is defined as the side adjacent over the hypotenuse. All right, again, let's multiply both sides by 4. And the 4's cancel here. And we have x is equal to 4 times the cosine of 30. So on our calculator, we can take 4 cosine 30, and we see that we have x is approximately 3.464. Okay. Now I do want to just refresh your memory about 30, 60, 90 triangles. The side opposite the 30 was an easy one to calculate. It's always half the hypotenuse. So the 2 was pretty easy to get. The side opposite the 60 degree, this is going to be our 60 degree angle. According to our 30, 60, 90 relationship, the side opposite the 60 is half the hypotenuse times the square root of 3. Now, if you want to check that, you can go ahead and take your calculator and do 2 times the square root of 3. And it should be, yes it is, it's the same value that we got when we used our cosine. But now when I write 2 square roots of 3, that's an exact value. When I have to use trig, I'm only going to be able to get an approximation usually. So my preference, obviously, is that we have the exact value. But what we've done here now is we've shown that this point in polar coordinates is the same as the point 2 root 3, comma 2 in rectangular. So this is my polar, and this is my rectangular. Okay. So whenever we give rectangular coordinates, we have x, y. Those are rectangular. And whenever we talk about polar coordinates, we have r is usually this value. It actually stands for the radius of the circle. If I were treating this like the hand of a clock that rotates around, that's our radius of that circle of rotation, those concentric circles that we had. So r, whatever this little symbol is for this textbook, and then theta. So r theta is our polar coordinates. And we'll be able to get a relationship between those two.